Hi, everyone. My name is Matthew Liu. I'm a fifth-year chemical engineering PhD candidate at Stanford University, where I study with Professor Will Tarpe. Now, I first studied chemical engineering in undergrad at UC Berkeley, where I first researched the oxidation of atmospheric aerosol before researching the electrochemical carbon dioxide reduction reaction. And that's what really sparked my ongoing interests in electrochemistry and electrochemical engineering. Now, in grad school, I transitioned from studies of the air to the water, and in particular, nitrogen pollution in the waters, because humanity has profoundly skewed the nitrogen cycle, and we're now outputting far more reactive nitrogen into the environment than we're able to remove. And this imbalance largely comes from how we produce and use ammonia as a resource. We spend 1% to 2% of global energy and carbon dioxide emissions to produce ammonia, but let a lot of it go to waste. And this has devastating impacts on ecosystems, the environment, and ultimately costs our government billions of dollars a year to remediate. So to begin restoring balance to the nitrogen cycle, my work looks at electrochemical reactive separation processes that achieve selective separations and selective reactions. This helps not only remediate nitrogen pollution in wastewaters, but recover those so-called pollutants as high purity products for further use in agriculture, chemical manufacturing, or as an energy source. So in my PhD, I've designed electrochemical membrane reactors and processes using these reactors to separate one component out of a wastewater, which is a complex and variable matrix of constituents. For example, in this picture, electrochemistry is used to precisely dial in the driving force for ammonia migration from the left to middle chamber and dial in the pH in the middle chamber to allow volatile ammonia to go from the middle to the rightmost trap chamber and capture ammonium sulfate, a high purity commodity fertilizer. Now, on the reaction side, I've studied three types of reactions: heterogeneous, homogeneous, and single atom catalysis. And each have their intrinsic pros and cons. With heterogeneous catalysts, you already have your separations achieved. Your catalyst is set in a separate phase from your reactants or products. But a key challenge is understanding how surface structure impacts reaction performance. Conversely, in homogeneous catalysts, we have atomically precise active sites, but we have the challenge of separating that catalyst from the reactants and products. Meanwhile, in single atom catalysis, we leverage benefits of both heterogeneous and homogeneous catalysis. And this represents a frontier in electrocatalysis. So thanks so much for listening to my presentation on electrochemical reactive separations. I would like to acknowledge my professor Will Tarpe for his generosity and time. And thank you so much to the ARCS Foundation for funding this work.